In an old version of the lab we're going to do Wednesday, I had some of the solutions listed, and some of them said 3.0 M, and some of them said 0.1 M. So knowing what we know now about molarity, which one would be the stronger one, 3.0 or 0.1? 3.0, that's right. As the number gets bigger, that means you have more solute, all right? And so a 3.0 M solution would certainly be stronger than 0.1. And at the time when we did this, like most of the solutions are fine at 0.1, but we had better results at 3.0. And I think now we've changed it. But if you happen to see on the bottles on Wednesday, like 3.0 M or 0.1 M, you know what they mean now, all right? Most of the chemicals we'll use on Wednesday are 0.1 M, but some of them I think are still 3.0, but anyway, you'll know what they mean. And 3.0 is just more bang for the buck. Anyway, all right, so molarity, moles over liters, grams to moles using molar mass, 1,000 milliliters in a liter, so 250 would be 0.250 liters to get these numbers. And again, the bigger the number, more bang for your buck. The smaller the number, less bang. There are other kinds of concentration units, and percentages is a different one. We'll look at different ones more in Chem 222 than this term. Molarity is kind of the chemist's right-hand man, all right? It's the one that we go to almost all the time. And in our own stockroom, most of our solutions are listed as molarity. We do have some that are percentages and different kind of things, but most of them by far are molarity. And they're really, really helpful, like we'll see here in a little bit. Now, one thing about molarity in ionic compounds is that as they dissolve, they break up into cations and anions. And copper 2 chloride is a good example of this. So copper 2 chloride is a strong electrolyte. And again, that just means that if you put 1 mole of CuCl2 in, they're all going to break up. You're going to end up with moles of copper 2 plus and moles of chloride. However, an interesting thing happens with molarity, all right? In copper 2 chloride, you have 2 Cls for every CuCl2, and that's why we have 2 Cl minuses. But this affects the concentration of chloride. So let's say that we had a copper 2 chloride solution which was 0.30 moles per liter. So that means that if we had a liter of this stuff, 0.30 moles would be copper 2 chloride. Well, the copper 2 plus to copper chloride solution is 1:1, like there's a big 1 in front of those. So that means that if this was the solution concentration of the whole thing, we would have 0.30 molar copper 2 plus. But chloride is twice that concentration because we get 2 Cl minuses off for every 1 CuCl2. So if you have, here's another way to think about this. If you have 0.30 M, that means in this case 0.30 moles CuCl2 per liter. All right, remember big M just means moles per liter. And the balanced reaction here says that for every 1 mole CuCl2, you'll have 2 moles Cl minus. So I'm really just using a stoichiometric equation, like we did in last Monday, that says that 1 mole of this creates 2 moles of chloride. So the moles of CuCl2 will cancel out, and 0.30 times 2 means 0.60 moles chloride per liter, which is 0.60 M chloride. So I put this in here because, like, let's say you had a diet which was sensitive to sodium. All right, some people can't do a lot of salt. Well, you put in NaCl, and that's 1:1. But if you had like sodium oxide, for example, that's Na2O, and 1 mole of Na2O would create 2 moles of Na+, so you get twice the amount of sodium that you might think you did. So knowing these ratios has big applications, all right? In terms of health, you might get extra sodium when you didn't want extra sodium. In this case, you would get extra chloride, maybe more than you thought. Like you thought it was going to be 0.30, and you ended up with 0.60. So the solution, the stoichiometry of the molecules becomes pretty important in figuring out what the ion concentrations are. Any questions on that? Okay. Oh, go ahead.
So I was saying that there's 0.6 molarity of CO2, like in what? In the whole global?
Another good question. So let's make sure we're clear on definitions here, first of all. Cl2 is when you have pure chlorine gas. And pure chlorine, like chlorine is number 17 on the periodic table. So if you have chlorine with 17 protons and 17 electrons, then that's when they make Cl2, okay? So like if you've ever seen a tank of chlorine, that's Cl2. This, though, is not pure Cl because this chloride has an extra electron. So it still has 17 protons, but this version has 1 extra electron. So this one actually has 18 electrons. Chloride is different than chlorine, okay? So this isn't chlorine. We don't have to worry about the Cl2 part. That's why we're writing it here as Cl minus. And any time you have chlorine with a metal, it'll be like this. It'll be the -1 version. So with that being said, then yeah, you're thinking about this is breaking up not into Cl2, but it's 2 Cl minus. Like the negatives don't want to be real close to each other. So I like what you're thinking. Yeah, the Cl2 is breaking up. It's not really Cl2 though in my world, all right? Those are 2 Cl minuses, which I know is kind of silly and maybe subtle, but the extra negative electron will keep them from each other, like negative charges repel, okay? So good. So I'm glad you brought that up. Chlorine by itself with just the equal amount of protons and electrons will be Cl2. But when you're with metals and when you're with most nonmetals, any kind of compound really, it's probably going to be more like chloride, the Cl minus version. So we'd say there are 2 chlorides for every 1 Cl2. Good, excellent. I'm glad you brought that up. Other questions? Love your questions this morning. All right. Here's an example. This is with barium chloride, all right? And we have here a 0.12 molar barium chloride solution, all right? And so again, what this means is that in a liter of this stuff, which is about 1,000 milliliters, you would have 0.12 moles of BaCl2. Now, what is the relationship between the barium ion and BaCl2 in this formula? Like, is it 1:1, 1:2? 1:1, that's right. Looking at the formula, there's 3 atoms in this thing, all right? One of them is barium, and there's 2 Cls. So you're going to have 1 barium for every BaCl2. And why that's kind of cool, the concentration of barium will also be 0.12 if it's 1:1. So of the answers here, it's not going to be D because the barium concentration's wrong. 0.12 is going to be the barium concentration, and it's because BaCl2 dissociates into a barium 2+, 1:1. Good to go. Now, the next one goes back to your cool question about chlorine. Remember that this is chlorine with a metal. This is chlorine in a compound. So it's not going to be Cl2, all right? Cl2 would be the version if you took the electrons away from chloride. Chloride has an extra electron. That's why it attaches itself to the positive barium. So this last answer also isn't right here because it's not pure chlorine we have. This is chloride, okay? Now, if we have 1 mole of barium chloride, that means we have 1 mole of barium and 2 moles of chloride, 2 moles of Cl minus. So for every 1 barium chloride, how many chlorides are we going to have? 2. And if you have 0.12 moles barium chloride, how many moles of chloride will you have? 0.24. That's right, twice the barium. So just like you went from 1 to 2, 0.12 goes to 0.24. And that's going to be your concentration then of the chloride. It's a 2 chloride to 1 BaCl2 ratio. So you multiply the chloride, or barium chloride, number by 2 in order to figure out the chloride concentration. And again, that's very cool. It's not Cl2 here because it's not just chlorine by itself. It's chlorine with a metal. So we think about it as chloride. Any questions on that? Cool. All right. Molarity is super, super common and very helpful to chemists. So I told you that this week's lab was net ionic equation and stuff like that. The next lab, the unknown chloride lab, will use a lot of molarity and how moles can be used, and percentages and stuff like that too, by the way. I want to show you some examples of how this all works out. And we're going to start off with an example of oxalic acid. Now, oxalic acid is a nasty little compound that you can't actually buy in a jar and stuff. Anyway, oxalic acid is H2C2O4. And notice that in this acid, we have 2 H's listed first. This is what they call a diprotic acid, which means it has 2 H pluses that come off. So this is pretty powerful stuff. But anyway, in this problem, we want to make 250 milliliters of a 0.0500 molar solution. And the question is, how much oxalic acid do we weigh out from the bulk container and add to 250 milliliters or so of water to make this solution? And that's no problem. Well, earlier, which I erased now, how convenient, I had molarity, big M, equals moles over liters, moles over volume. On a problem like this, it's very helpful to think about the moles needed as equaling molarity times the volume. If you have molarity, which is moles per liter, and you multiply by liters, that's going to give you the moles. So if we can take the molarity here and multiply it by the volume, that's going to give us the moles. Now, if molarity is moles per liter, what do you think the units are going to have to be of the V part here? Can we use milliliters for the... No, good. We need to use liters, all right? Moles over liters times liters. The liters will cancel out, and you're going to have moles. So again, earlier I told you how many milliliters are in the liter. How many milliliters are in the liter? 1,000. Thank you for paying attention. Yeah, 1,000 milliliters per liter. We're going to use this a lot, all right? So we got to turn the milliliters into liters, and that's going to be our V. V times big M is liters times moles per liter. That's going to give us the moles. And for moles, we can use the good old molar mass to take it into grams. Let me show you how that works. So first of all, find the moles, all right? And again, milliliters to liters. I know you're going to get me sick of me hearing that. 250 means 3 sig figs, all right? Don't forget that. So 3 sig figs, 0.250 moles per liter. The molarity, 0.0500. Multiply them together, 0.0125 moles. That's the moles of oxalic acid we just figured out. And moles to grams is what we use the molar mass for. So we got to figure out the molar mass of H2C2O4. 2 carbons, 2 times 12, plus 4 oxygens, 4 times 16, plus about 2 times 1. It's about 90 grams per mole. So that number times the moles required, 1.13 grams. So if we measure out on one of those scales 1.13 grams of this oxalic acid and put it in 250 milliliters of water, we're going to end up with a 0.0500 molar oxalic acid solution. Any questions on that? Cool. just remember to go from milliliters to liters. All right, once in a while I see people just spacing that part out, and it's really important you use liters here. But that's why I keep harping on how many milliliters per liter, and I'll say 1,000 for you this time. You don't have to answer me, but I will say it more just because I want this to make sure it's in your brain. So, okay, yeah, go ahead.
Gram what?
The what?
Grams what?
What is the solute here? Look at
Acid.
oxalic acid. Yeah, that's right. Almost always in our class, the solvent will be water. All right, not all the time, but most of the time. So in this case, then, it's if we're looking for a molarity, it'll be moles of oxalic acid per liter of solution, and oxalic acid is the solute. So we're after here the grams of the oxalic acid. Yeah. So it would be 1.13 grams of oxalic acid in a total of 250 milliliters of water, and that'll make this 0.0500 molar solution. Excellent question. Any other questions? All right. There's
To
two.
prepare our solution using the dilution method, we first obtain 2 milliliters of stock solution with a pipette. Filling the pipette with stock solution to the mark on the pipette ensures that we have 2 milliliters of this solution. We add the 2 milliliters of more concentrated solution to the 500 milliliter volumetric flask, touching the side of the flask with the pipette. We add water to the mark on the flask. After mixing thoroughly, we have exactly 500 milliliters of a solution with a concentration of 1.60 times 10 to the minus 4 moles per liter.
If you're in the lab and you want to make a solution, there are two main methods that chemists use. And the example with the oxalic acid we just did is an example of the first one. So we weighed out, we figured out how many grams of the solute oxalic acid we needed. We put it in about 250 milliliters of water, shook it up, and that's that way. All right, you have to measure out the mass of the solid, et cetera, et cetera. However, another way which is really common is to take a concentrated solution and make it more dilute. And a lot of the chemicals that we use in lab, for example, hydrochloric acid, sulfuric acid, nitric acid, as well as usually sodium hydroxide, potassium hydroxide, what we do is you'll buy these chemicals from a company and they come like really concentrated. So like earlier I said how we used 0.1 versus 3.0, and 3.0 was much more concentrated. Sulfuric acid, if I remember right, comes as an 18 molar solution. I mean, that is really, really powerful. I can tell you funny and sad stories of my own behavior with that other times. But anyway, an 18 molar is way more than most chemists would ever need because it's got too much energy, all right? And most of the time, we use less or more dilute, smaller number of molarities because they're easier to manage. So what I'm going to do now is talk about the other method that's used to create solutions. And it's mostly used for acids and bases because they'll sell these in these really concentrated solutions. And it's up to the chemist then to create a more dilute and more usable concentration, like taking an 18 molar down to a 3 molar or 0.1 molar or something like that. Now, when you dilute a solution, you take it from a more concentrated solution, you add a little bit of the heavy stuff in, and then you add a lot of water. And the question is, of course, how much water do you add? And that's a good question. Notice in this solution, which has a color associated with it, this is a stronger color, and this, of course, is a more weak color. And that's another thing you see sometimes on the solutions if you dilute them. If they have a color, then you won't see like as intense. In my Kool-Aid, like if I did like grape Kool-Aid or something, the grape Kool-Aid that was concentrated was a really dark, intense purple, but when you add lots of water to it, it becomes less intense, less purple. All right. I didn't do very well in art, so I'm probably describing my colors horribly. I apologize. But anyway, here's an example of a dilution question, all right? So let's say that we came into the lab and we wanted to have we wanted to have 0.50 molar sodium hydroxide. And that's fairly concentrated. But anyway, we'll say that the stockroom forgot to do it, and so we have to do it ourselves. And the stockroom doesn't have, right now, any 0.50 molar sodium hydroxide. But when we're digging around the stockroom, we find 50 milliliters of 3.0 molar sodium hydroxide. So we can turn 3.0 molar NaOH into 0.50 molar NaOH if we add water. But the question is, how much water do we add? Stuff like that. So this is a type of a question where you're taking a concentrated solution and you're diluting it down to a more usable type of solution. And if you do this, because most of our solvents are water-based, like I said earlier, what you want to do is you want to dilute the solution. You want to add some water. And adding water will make the 3.0 number smaller. And we want to add just enough water so that we end up with 0.50 M. But the question becomes, like, how much water do you want to add, obviously? Like, you don't want to add too much water, so this number would be less than 0.50, but you want to add enough water. If you added less water, then we might end up with like 0.7 moles per liter. So we can figure this out knowing the definition of molarity, because molarity is just moles of volume equals moles of volume. So in this kind of problem, it's important to remember that the moles in the concentrated solution equal the moles in the dilute solution. And these little pictures right here are kind of dorky, but the number of yellow pieces right here, and yellow's like the solute, okay? The number of yellow pieces here equals the number of yellow pieces over here. But obviously on the right, there's a lot more room for them to spread around. But the moles are the same. So the moles in the original solution equal the moles in the final solution, the final dilute version. And as we saw on the earlier slide, moles equals molarity times volume. So a real handy kind of way to do this is just to remember that molarity times volume equals moles. So we started with 50 milliliters of 3.0 moles per liter. Now I turned 50 here into 0.05, that should be 0.0500, sorry about that, liters. 50 milliliters is 0.05 liters, times 3 moles per liter. That means we're starting with 0.15 moles of NaOH. And that number is not going to change if we're just diluting the solution. We're going to change the volume of liquid, but we aren't going to change the moles of the solute. So that means that our final solution is also going to have 0.15 moles per liter. Now remember that in this example, we want 0.50 M. And 0.50 M means 0.50 moles of NaOH per liter of NaOH. So once we know how many total moles we have, moles divided by moles per liter is going to give us our new volume of solution. So moles divided by moles per liter, or moles times 1 liter over 0.50 moles. Remember, this is nothing more than molarity. 0.50 M means 0.50 moles per liter. I put the moles on the bottom and the liters on the top. The number that pops out, 0.30 or 300 milliliters, that's going to be the volume of our final solution, all right? Our final solution of 0.50 M is going to have a total volume of 300 milliliters. Any questions what I've done right here? The important part here is that the moles that you start with equal the moles that you end with. And moles equals molarity times volume. So we first found the moles that we started with, moles of solute, the NaOH in this case. Once we knew that, I divided by the final concentration to give the total volume of this final solution, which is 300 milliliters. The only thing tricky on this is that we already have 50 milliliters of solution. So how much water do you think you're going to want to add if we want, at the end, 300 milliliters, but we started with 50 milliliters? 250. Well done. You want to add 250 milliliters of water. And that, combined with the 50 milliliters we started with, will make a total volume of 300 milliliters. That's going to be the way to go from 3.0 big M to 0.50 M. We diluted it with water. We're going to add 250 milliliters of water to make a total of 300 milliliters. That'll make our final concentration 0.50. Any questions on that? Okay. These kind of calculations pop up enough that this next little thing is super handy. And instead of talking about moles at the beginning and moles at the end and blah, 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 people will usually use what I call M1V1 equals M2V2, or MIVI equals MFVF, or C1V1, C stands for concentration, C1V1 equals C2V2, but it's really, really handy. Now remember, molarity times volume equals moles. So what this is saying is that the initial moles equals the final moles. And if you have 3 of the 4, you could plug in to find the 4th one. So on that last example, M initial was 3.0 M, and V initial was 50 milliliters. And the M final, what we wanted was 0.50. So we solved essentially for VF, the final volume. It came out to be 300 milliliters, which we then converted to 250, et cetera, et cetera. But the reason I like this so much is that as long as V is the same kind of unit, you can use liters or milliliters. And that's why this is a lot handier. So in the last example, I made sure that we went to liters from milliliters, so 50 milliliters, 0.05 liters, and the final came out to be 0.30 liters, which we converted to 300 milliliters. Hey, you don't have to do that with this equation. You can put the 50 in there, and you'll get 300 out. That means 300 milliliters. So lazy chemists of the world unite. We're always trying to figure out ways to save a step, all right? And if you use M1V1 equals M2V2 or MIVA equals MFVF, etc., then you can use liters or milliliters. Just make sure they're the same type of unit, all right? And that can be pretty cool for a chemist. Questions? Yeah.
Is this called titration, or is this something different?
This is preparing the solutions for titration. Yeah. The unknown chloride lab we're going to do is a titration, and I'll talk about that a little bit. So in a titration, you'll have solutions of a given molarity, and this is about how to prepare the solutions that you'd use in titration. It's not a titration per se, but it gets you ready for titration. I'll show you more on titrations here in just a second. Good. Excellent question. Titration is a word we'll use a lot all the way through Chem 223. It's a powerful technique that here at Mount Hood Community College, we can compete with MIT and Berkeley and all the cool schools with our equipment. It's something that I find it's really powerful. Anyway, there's a lot of things we can't compete with here at Mount Hood with MIT and Berkeley, but when it comes to titrations, I would argue we're just as good. I'm not biased or anything, really. Prop that back on. Questions? Any of that? Here's an example of how to use M1V1 equals M2V2 or MIVI equals MFVF, whichever one you like. In this example, we're having 60 milliliters of 0.25 molar HCl, and we're adding it to a 500 milliliter flask, and we're adding enough water to get up to that point, so final volume 500. And the question is, what's the concentration of HCl in the solution? Well, you can use whichever one you want. MIVI equals MFVF. I stands for initial, so initial molarity, initial volume equals, not the other MF, This is final molarity times final volume, okay? So in this problem, the MI, the initial molarity, 0.25, and the initial volume, you could take these all into liters, which is fine, but lazy chemists, 60 milliliters. If you use milliliters on the left, you must use milliliters on the right. We're trying to solve for the final concentration, the final molarity, MF, and the total volume, 500 milliliters. So in this equation right here, you would solve for MF. You would take in your calculators 0.25 times 60 divided by 500. You had molarity here, so MF will be molarity right there. This number comes out to be 0.030. So this is how you would use this kind of thing. In the problem we did, we had MF, but we didn't have VF, the final volume, so we solved for the 300 number from there. It works either way. Any questions on that?
Reaction of zinc and hydrochloric acid is both a gas-forming and a redox reaction.
In last Monday's lecture, we talked about stoichiometry. So for example, to find out how many moles of HCl we need, we would first figure out moles of zinc. 1 mole of zinc needs 2 moles of HCl, so we had like a 2-to-1 ratio. And that's a really powerful thing in chemistry. You can do the same kind of thing with solutions, because it really does come down to, in a reaction like this, a mole-to-mole ratio. And in this problem, all right, it says we're converting 10 grams of zinc into all this stuff, and we're using 2.50 molar HCl, so a pretty good concentration of HCl. And the question is here, what volume of HCl do you need? And this isn't too bad of a problem. Remember that a balanced reaction is absolutely important. The 1-to-2 ratio here of zinc to HCl is a mole ratio. It's saying that 1 mole of zinc requires 2 moles of HCl. So figure this out, we'll take the 10 grams of zinc, turn it into moles using the periodic table. A mole of zinc is going to need 2 moles of HCl, so we'll multiply the zinc by 2 to turn it into moles of HCl needed. The new part on the block now is that once you have moles of HCl, this number is moles per liter. So moles of HCl and moles per liter of HCl, we can use that to turn it into a volume. We'll turn it in initially into liters, which you can turn into milliliters. So this is like another tool in the chemist step, but it all comes down to that mole-to-mole ratio, all right? In last chapter, we did grams to moles to moles to grams a lot. This is grams to moles to milliliters, all right? The new thing now is we're just using this moles per liter value to turn moles into volume. Cool. So let's see how this works out. So the first step, 10 grams of zinc turned into moles. We'll need the molar mass of zinc. Zinc is number 30, 65.409 is what it looks like up there. For some reason, I use 65.39. I must be using an old version, whatever. You're going to get the moles of the Zn, which in this case is 0.153. So this is the grams to moles part of the grams to moles to moles. We just turned grams and moles. Now, we're after volume of HCl. So we're going to need a stoichiometric factor, which again is just the snobby way of saying moles of what we start with turned into moles of what we need. We want to get to moles of HCl, so we're going to use 1 mole of zinc for every 2 moles of HCl. So we had 0.153 moles of zinc. The reaction itself down here says 1 zinc for 2 HCl's, or a mole of zinc needs 2 moles of HCl. So that comes out to be 0.306 moles HCl. Questions on this 2-to-1 ratio? Everybody cool? All right. Now, the new part is about this molarity, and it's 2.50 M. And remember, big M just means moles per liter. So that's moles of HCl per liter of HCl. Here we've got moles of HCl in this reaction. So if you take the 0.306 and divide by 2.50 M, here I wrote it out as 2.50 moles HCl per liter of HCl, because I wanted you to see how the moles cancel out and you have just liters. So when you do all these steps, it comes out to be 0.122 liters or 122 milliliters of HCl. So if we took 122 milliliters of 2.50 molar HCl and added it to 10 grams of zinc, we wouldn't have any limiting reactants. We would have 100% completion in theory. We'd have just these two over here. So again, this is not grams to moles to moles to grams. This is grams to moles to milliliters or liters. All right, just another little trick in the chemist's arsenal of figuring out what happens. Any questions on that? All right. Now, as we talked about earlier, the main thing that we're focusing on in this section is what's called a titration. And titrations are super powerful when it comes to chemistry. A titration is a tool, a technique used in the analysis of compounds. You can find all kinds of information. You can find out, for example, if you didn't know the initial concentration of this, you could use the concentration of NaOH to backtrack to the concentration of oxalic acid. You can also find the molar mass sometimes of your unknown compounds and mass percentages. I mean, the list just goes on and on and on of all the things you can do. Really, really powerful. So to demonstrate what a titration is more, all right, where we use these solutions we were just talking about, let's use this particular reaction. And this is our friend oxalic acid, once again, that we talked about earlier. And we're going to take oxalic acid and react it with sodium hydroxide. Now, remember that any compound where hydrogen is listed first is going to be an acid. And a base is a metal hydroxide, like sodium hydroxide. So this is one of our acid-base reactions over here. It's an exchange double displacement reaction. And the H pushes the Na out, if you will. So the Na starts dancing with this oxalate ion, C2O4. H goes with OH to make HOH or H2O, which is water, and sodium oxalate. So when you have an acid-base reaction, the acid reacts with the base. The products are water and some kind of salt. So sodium oxalate here is the salt. And this is not salt you want to put on your French fries. All right? This would be a really nasty, actually, salt to put on it. But in chemistry world, a salt is the product of an acid-base reaction. So water and a salt are made. This salt is sodium oxalate. But anyway, this is the formula for oxalic acid. We'll talk about that later. We're going to look at this reaction as we talk about what a titration is. Notice the 2-to-1 ratio here of sodium hydroxide to oxalic acid, and that will be important coming up. Any questions so far? Okay. In a titration, we use what's called a buret, and it's basically a long tube with a little stopcock on the end of it. And the stopcock has an on when it's parallel to the flow. So like you can see that the liquid stuff will go this way. So right now it's parallel. This would make it open, all right? And when it's perpendicular to the flow, that means that it's off. And a buret is not the cheapest set of equipment, but it's very, very powerful. You get lots of significant figures associated with it. This is called a Buret Clamp. We'll use this in the lab, not this week, but next week. As the stuff from the buret goes into this, which is, by the way, an Erlenmeyer flask, there's usually some kind of a color change involved. And when the color persists, that means the reaction is done. In this particular reaction, they're using a type of an indicator to indicate that the reaction is base. This is sodium hydroxide in the buret. They're adding it in, and when the sodium hydroxide dominates, this color turns purple. That means you have a basic amount of more base around than anything else. So really, a buret, a titration, is nothing more than putting some kind of solution in the buret. You've got some kind of solution in the Erlenmeyer, And you add just slowly, slowly, slowly until you see usually some kind of a color change. That means you stop. And you can record the volume added. Volume of the titrant is the fancy name. And you usually know something about what's down here, so you can relate the volume added to the stuff that's down there to find molarities and concentrations and all kinds of interesting things. This is what we'll actually do 2 weeks, not this week, but next week, I guess, less than 2 weeks. Questions on that? There are many types of titrations too, so this is just a common one. We'll look at some other ones too. All right, so let's say that you have 1.065 grams of oxalic acid, and it takes up 35.62 milliliters of sodium hydroxide, and it reaches what's called the equivalence point. Equivalence point is when the solution turns color, and that tells you to stop. So the question is, what's the concentration of the sodium hydroxide solution? Now, oxalic acid, for different reasons, is a really good place to test your sodium hydroxide. You can see if it's good, and you can also tell how concentrated it is. So maybe the stockroom said it was such and such concentration. Well, is it really? Right? Because stockroom people make mistakes too, and I'm not mad at them for doing it or anything, but it's nice sometimes to double check. So this is a way we're going to double check what the concentration, if you will, of the sodium hydroxide is. Now notice here that we started with grams of oxalic acid, and we can turn that into moles of oxalic acid using the molar mass. From that, moles of oxalic acid times 2 will give us the moles of sodium hydroxide. That's the value of the balanced equation. And if you can figure out moles of sodium hydroxide, you can divide by the liters of sodium hydroxide to get the concentration, the moles per liter of the sodium hydroxide. So in a nutshell, grams to moles divided by this in liters, that's going to give us the concentration. Questions? To go from grams of oxalic acid to moles of oxalic acid, we need the molar mass. So in a little bit, I'll show you that number. That comes from 2 hydrogens and 2 carbons and 4 oxygens. And you can find that from the periodic table. So the moles of oxalic acid, I figured out was 90.04 grams per mole. So 1.06546 figs divided by molar mass. That means that we have 0.01183 moles of oxalic acid. So that's the amount of oxalic acid in our titration. And once you have moles of oxalic acid, we can use the balanced equation. And down here it says 1 oxalic acid needs 2 sodium hydroxides to react. So if we take that moles of oxalic acid and multiply by 2 over 1, remember this is the acid, this is the sodium hydroxide. So moles of oxalic acid times 2 over 1 will tell us the moles of sodium hydroxide needed to get to that equivalence point where we stop. So that means that 0.02366 moles of sodium hydroxide were added in to react with the 1.065 grams of oxalic acid. So it's kind of like grams to moles to moles. But now what we're going to do in the next step is we won't go like moles to grams or moles to milliliters. We already know the milliliters that are there. So we're after the concentration, the moles per liter. We've got the moles. We'll divide by the liters here in a little bit, and that should get us to the molarity, the concentration of the NaOH. Any questions on this so far? Okay, so grams to moles, moles of acid to moles of sodium hydroxide. The last step, moles of sodium hydroxide divided by the liters of sodium hydroxide used. And this number comes from 35.62. 35.62 divided by 1,000, 0.03562, moles over liters gives you the molarity, 0.6642 moles per liter. So our concentration of NaOH, 0.6642. And if we wanted 0.6642 and that's what we calculated, cool, everybody's good to go. On the other hand, if the stockroom was supposed to make 0.5 and this is what it ended up, well, got to compensate a little bit, but this is a nice way just to check, all right, to make sure that you're good to go. So again, what we did, grams of oxalic acid to moles of oxalic acid. We used the balanced equation to go from moles of oxalic acid to moles of sodium hydroxide. Moles of sodium hydroxide divided by the liters of sodium hydroxide used. We converted milliliters to liters. Molarity, how many milliliters in a liter? 1,000. Thank you for bearing with me, but this is really important. 1,000 milliliters per liter. Yeah. Any questions on that? So this technique, like I said, is really cool. If you have a solution, maybe it's older, maybe you don't trust the stockroom people, whatever, it's a nice way to check to see what your solution concentration is. You can start off with something like oxalic acid and then figure out these numbers just to verify, all right? Because when you're, doing research and stuff like that, or even just a reaction for a good grade, it's nice to know the reaction concentration so you use the right amount and stuff like that. So now that we know this sodium hydroxide solution to a lot of sig figs and pretty accurately, we can do some kind of cool things with it, all right? So let's say that one of you says, oh, I'm going to bring my instructor an apple. And in the old days, I think this used to happen, it's like, woo, apple a day keeps the doctor away. I don't know what you're using an apple for, but apples have inside them a little bit of what's called malic acid. Now, malic acid, C4H6O5. The hydrogens are not listed first here, so it's hard to tell from this formula what the acidic hydrogens are, like all 6 or just 1. Well, malic acid is actually a diprotic acid, which means it needs 2 sodium hydroxides to react with 1 malic acid. Malic acid makes the malate ion, which is nothing you need to worry about, but notice how 2 of the hydrogens went away. And as the 2 H pluses went away, 2 Na pluses came in to take its place. So malic acid needs 2 sodium hydroxides to make sodium malate, which we don't care about, and 2 waters. This is another acid plus base making water plus salt reaction, just a little bit different kind of variety. Now, when you take a bite of an apple, your mouth doesn't go, ow, like you're biting into something acidic. There must not be a lot of this acid around. So let's say that we took 76.80 grams of apple and we mashed it all up and we titrated it, all right? We titrated it with sodium hydroxide and we're using our 0.6642 molar sodium hydroxide from before, all right? It needs 34.56 milliliters of that sodium hydroxide to reach the end point. So we can actually use this to find the weight percent of the malic acid in the apple. Now, weight percent is going to be grams of pure malic acid divided by grams of sample, 76.80 times 100%. Kind of what we did with the KClO3 lab from this week. You found grams of the pure KClO3, divided it by the total grams you put in times 100. This is similar kind of thing, but now it's going to be grams of pure malic acid divided by the total times 100. So this is a similar kind of a problem to that, but we're going to figure out the weight percent of malic acid. And again, acids, when you take a bite of an apple, it doesn't really feel like it's acidic, so it should be a relatively low number, but we can actually calculate something like that using this technique. Any questions on this problem before we look at it? All right. In the last problem, we went grams of acid to moles of acid because we knew what it was, moles of acid to moles of base divided by volume gave us concentration. Here, we're going to use similar parts, but here we've got volume of base and concentration of base. So if we turn this into liters, liters times moles per liter will give us moles of the NaOH. And then, using our balanced reaction here, 2 moles of NaOH come from 1 mole of the malic acid. So we're going to use a 1/2 ratio to go from the NaOH to the malic acid. And once we know moles of malic acid, we can figure out the molar mass to get grams of pure malic acid. That'll be a number hopefully much smaller than 76.80 because the weight percent will be grams of the pure stuff divided by this number times 100%. Okay, so first, moles of sodium hydroxide. We'll take the concentration, 0.6642, which is moles per liter, and we'll multiply it by the liters of the sodium hydroxide. So if you take this and divide by 1,000, 0.03456, this comes out to be 0.02295 moles of sodium hydroxide. So when we did this titration, the 34.56 milliliters basically delivered 0.02295 moles of sodium hydroxide. Any questions on that? Cool. Once you have moles, that's where the balanced equation comes in. Because remember, this 1, 2, 1, 2, those are all mole ratios. And so since we're starting with moles of NaOH, and we want moles of the malic acid, in the next step, we're going to have 2 moles NaOH on the bottom and 1 mole of this malic acid on the top. So taking that number and multiplying it by essentially 1/2, all right, where here the acid is the malic acid, the C4H6O5 thing. 1 mole of acid needs 2 moles of base. So since we started with moles of NaOH, they'll cancel out. We'll have then 0.01148 moles of malic acid. So again, it's kind of cool. We started with 34.56 milliliters, used the concentration to get moles of NaOH, and then using the balanced reaction, we took the moles of NaOH that we used and turned it into moles of malic acid that were in the apple. And in our sample of apple, 0.01148 moles of malic acid. Any questions on this? Sweet. Now, the weight percent, again, is going to be grams of pure acid divided by grams of sample times 100%. The 76.80, that's the grams of sample. That's our denominator. So we need to turn moles of the malic acid into grams of malic acid. So for the next step, we're going to need the molar mass of this C4H6O5 thing. And if you figure out what that is, the molar mass, 134.1 grams per mole. So we took the moles of the I should say sodium hydroxide, sorry. Well, it's equal, yeah. Moles of malic acid into grams of malic acid. This number is the molar mass of the C4H6O5. So to get this number, 4 times 12 plus about 6 times 1 plus 5 times 16. And that's where I got that number from right there. So in the malic acid, in the apple, there was 1.539 grams of the pure malic acid. We put 76.80 grams of apple in. So to find the percent of malic acid, you'll take the grams of the pure acid divided by the grams of the whole sample, 76.80, multiplied by 100%. 2.004% of this apple is malic acid. All right? So our apple this is another type of percentage, by the way, a 2.004% malic acid. Okay. Any questions on this? All right. So titration, just to summarize, you use a Buret, and the Buret has underneath it usually an Erlenmeyer flask. And the burette's just a way to have controlled volumes of some kind of solution, all right? So in this problem, they used a burette. In the burette went the 0.6642 moles per liter sodium hydroxide. And this number came from the burette itself, all right? They actually measured out 34.56 milliliters of it. Now, they added this much in because apples have malic acid. And the 76.80 grams of apple that they mashed up needed this much to make a color change or something like that. So we went milliliters of NaOH to moles of NaOH. 2 moles NaOH to 1 mole of malic acid gave us the moles of the malic acid. And moles of malic acid times the molar mass, lots of M words. Moles times molar mass gave you the grams of the malic acid, the pure malic acid. So the percent of malic acid, grams of the good stuff divided by grams total, this divided by that, 2.004% malic acid. Okay. Any questions on that? All right. I just have a few more slides, but I'm going to wait till next Monday. The last slides are all on pH and stuff, and that's part of problem set number 5, so you should be good to go. You guys are awesome for being here. Thank you. Have a wonderful day. I will see you on Wednesday.